Welcome everyone to this week's IPLD sync meeting. It's May the 18th, 2020. And as every week, we go over the stuff that we've done in the past week and then discuss open issues we might have or answer questions and so on. And I need to open the hackpad. And so I start with myself, what I've done and will do. So on the Rust IPLD side, just a link to there is another implementation of Rust IPLD, which is kind of interesting because it's using Serde for serialization, but from talking to the person that did it, it's really done in a good way. So I'm still need to check it out more closely, but it's just a bit of a different approach. And feel free to check it out. I will definitely have a closer look at it. And other than that, I haven't done much IPLD work the past week. Mostly done Filecoin stuff and other things. But as promised for Chris, I've looked into the graph sync stuff and what the state is. Currently, there's really, as far as I can tell, there's only stuff going on really in the Rust world. And also there seems to be more parties interested, but now it really boils down to the chain safe, the people that work on the Rust Filecoin implementation called Forest, worked on selectors and now move on to working on GraphSync. So there will be a Rust implementation of GraphSync. And then on the JavaScript side, I haven't heard anything. So so that's basically it. So it started as so many people excited and wanted to do something, and now it's basically just the one implementation. It seems, yes, but of course, if I hear anything else, I will update you on this one. But it might be still interesting to check up with those folks, because they probably will also find issues or interesting things, or I expect that also perhaps even the spec might change if we haven't done the implementation of it. We'll see.
Okay.
I think that's all.
I have a question about that real quick. Can I ask a question about that?
Yes, sure. Yeah.
So I'm okay with like jumping in on the Rust graph sync efforts, or at least monitoring them. So if there's a stand-up meeting or weekly sync meeting that I can join, is that possible, or is that private, or what?
There is no meeting. So it's like because they concentrate on Filecoin, so therefore they are not interested in integrating it into IPFS, but they only do the Filecoin stuff. So I hope that, for example, Rüdiger from Actix is interested in IPFS, and I think he is, but I haven't heard back from him yet. So I hope that basically he will kind of look over it and see like how it relates to IPFS and make sure that it also works there. But I don't know, I can tell. So the only really thing that is happening is that the chain safe people, and they basically just do it. So, and if they have questions, they just ask random people, and that's mostly it. So there isn't any like structured way of dealing with it.
Are they going to open source their graph sync implementation, or is that closed source?
No, like they work in the open. So also like all the stuff is open. So
is there a link to their repo you can provide?
Yeah, so that's I can post it in the notes, and so it's just like on their Filecoin implementation. So it's not a separate repository, but just on their Filecoin stuff. I will put it into the
that probably kind of simultaneously explains why they might not be having a ton of meetings and process around it. They're doing it with this one very specific goal in this one repo, and like,
well, maybe okay. I mean, that's really helpful to know where things are at. It almost seems like I need to kind of let the dust settle a little bit. But I guess, Volker, if people come back around and, are trying to do more with GraphSync and IPFS or whatever, let me know. Because I'm interested in helping out. I just don't know. I don't know how much progress I'm going to make by myself without anyone else to talk to about it. So.
I don't know if you saw some of these discussions in the IRC channel lately, but we did have a bunch where I think it was someone from that same project is also really worried about making sure we have test fixtures come out of the selectors part, which is one of the big prerequisite steps towards GraphSync. And I don't remember if we got those pulled out into another repo yet, or if they're just ready to. But there's a bunch of nice JSON spec files that we talked through that have like super literal vectors for defining what the selectors should do. And so I'm really excited about those. If they're not in another repo yet, you can maybe copy paste them and, I don't know, poke that person in IRC more. I'm planning to retrofit a bunch of the Golang tests to use those as well, because it's a better format than the hand roll tests I've got right now. So.
Okay, thank you.
Small victories. Okay, should I just continue then?
Yeah, it was just, no, the silence was just because that's the link to the repository of the test vectors. I just
Yay!
Yeah, so, okay, yeah, so please go on, Eric.
Ainsave/IPLD test something. It's off my screen already, but yep, that's cool and good that that exists. So I don't have a ton more to report for myself this week other than discussions like that continuing and being really awesome. I've had a lot of non-technical things to worry about lately. So that's been fun. GoIPLD Prime is starting to sprout a changelog document now, which it's probably well overdue for. There's enough tagged releases now that I don't remember what they mean, so I'm starting to take notes. And also put some accumulated planned changes in there. Trying to be a little more intentional about racking up changes that are going to require any sort of refactor from consumers before I just hurl them out. So this document is going to be, at least for now, the place for those to reside. And yeah, that's about it.
Thanks. I'm doing too many things at the same time. Oh, I see things from Johnny. Please give us an update. Cool.
Yeah, howdy y'all. So I've been working on CBOR, quite a bit, DAG CBOR, and specifically signing things with Coze. So CBOR signing. And so I think I put a link in here with what I'm working on with the DID, the Decentralized Identifier specification. So I use IPLD on IPID. So IPID is basically publishing the IPLD as a specific formatted document, which includes the key, the cryptographic keys to the IPNS namespace. And then that basically is formatted did : IPID : and the hash of the public key, which is basically now your identifier. And so there's a whole bunch of work going on as far as mostly about resolving between different DID methods. And I, of course, think that, DAG CBOR, aka IPLD, is a superior method, but actually I needed to get it into the DID core specification. So I have an active pull request, and mostly centered around what's like a native CBOR representation, and then really a more specific DAG CBOR representation, which is IPLD. And the only issue I really have right now is with, and I mentioned this before months ago, is that when you strip away all the other tags other than tag 42, then it disrupts the ability to do CBOR, Coze tag 98 signing with semantic types embedded in the tags. And I'm still kind of struggling with this. There's probably ways around this with just basically signing things other than DAG CBOR and not using tags. But if you get a chance to do, please read my pull request, and I'd love any feedback. This builds upon what I was working on with that paper for the rebooting Web of Trust that never happened in Argentina.
If you're making a new codec entirely, you could set up entirely new rules as well. So It doesn't have to be DAG CBOR. It could be DAG Coze with a relationship to DAG CBOR, but different rules about tags.
Yeah, I think we actually mentioned that a few weeks ago, which basically like, yeah. So and then actually, I think there may have been a multi-codec for Coze in the works. So maybe I need to check that out.
So they were merged in the table, I think, weren't they, Volker? So we have
I
DAG
was
Seaboard,
just
the
about to
DAG
say
codes.
this, and here's
Sorry.
the link. Yes, they got merged.
Perfect. Okay, that's what I need.
Yeah, so we
That's
have
why I joined the call.
yeah, so
That wasn't you though, was it, Johnny? It was someone else. So are there overlapping efforts here?
I think there are. I know. So the 3box people actually are also picking up on this idea of DAG, signing DAG Cbor with Coze. And so I've been seeing a lot of that. So, and that comes out of like, so the previous rebooting of the trust, I actually talked about IPLD as being the native format and how we actually do this. And Christian Ludsvitz and I actually wrote a paper together from the Toronto meeting. And that's, I think, migrated into 3box.
Okay.
Yeah, so there is now a codec for DAG Cozy and DAG Chozy, or however you pronounce them. So for the Cbor and the JSON one. Yeah.
That's perfect. That's exactly what I needed.
And
Cool.
so we don't have any specs for those things yet. So, but I guess, yeah. So if anyone wants to, because I guess it's, so as I understood it, it's basically mostly DAG Cbor plus this additional tag, basically, more or less. Probably the codec. Yeah, but as Rod mentioned, you can come up with anything. So you could, for example, also allow all other tags as well. Or, yeah.
Yep. And then the write-up, I actually just basically just spelled out Cbor and the semantic types for tagging, but then beneath that, I actually added a section as far as DAG Cbor being a more constrained flavor of Cbor. And I think I specifically, I spelled out all of the constraints. For instance, keys can't be integers, they can only be strings, deterministic ordering in the representation, and only using tag 42 for it to be DAG Cbor. But I would love to make sure I'm not missing anything as far as, I know floating points can only be, was a bit 64-bit encoded. And so just if you could give it a read over, make sure I didn't miss any harder constraints that actually would make it specific for DAG Cbor.
Floating points are tricky because we have two different rules at the moment that we need to unify.
Right. And I think if I just said that if basically we just say all floating point will be 64-bit, I think that takes care of it, but let me know if that's not the case.
So it doesn't at the moment because JavaScript will do small as possible and Go will do 64-bit. That's a discrepancy we have to resolve with DAG Cbor. And we haven't we haven't decided which way we're going to fall on that yet. Because it's really hard.
I'm not supporting the 64-bit fixed size at all, despite having written that code. I do not actually believe that it's correct, just so that's clear. Not supporting it at all.
Okay.
So, yeah, right now, basically, the recommendation with DAG Cbor is don't make floats.
Which is fine, because I think the DID documents don't require floats. It's very much just cryptographic key material. And I think if it's not going to be that urgent for me to figure that out. But I think if I actually have something that basically, for the time being, sticks, then that I think will give me far enough along that actually gets some traction.
So it depends. So what language are you doing this in?
Mostly Go and Rust.
Yeah, I probably for now stick to the Go version of 64-bit, and I guess we'll remember to loop you in if we make a decision that goes a different way on that, or if we try to make a decision.
Just switch to the NVIDIA new stuff, and equal inconvenience for everybody.
The new float format from NVIDIA. Yay.
Okay, so coming back to
actually it's funny because actually I ran into that too. I'm doing some machine learning stuff, and NVIDIA, I have an older cards, and so that actually it automatically converted to 32 base, and so totally screwed me up.
Okay, Yeah, then next on my list is Rod.
Yep. Hang on, I'm just going to take one more note here. Get this out of my head. I'm trying to recall the highlights of what I wanted to talk about today. Okay, so I've been doing this Bitcoin thing, and I keep on, as I progress, I keep on thinking, what is this all for? Who's going to consume this? But it's for archival purposes, really. It's to say we can take the Bitcoin blockchain and preserve it in a form, in a content addressed form forever. And so that means that this is not just a project to let's make something that is practical. We have to make it practical across the entire blockchain. So I've done that, but I keep on, as I process the entire blockchain, I keep on finding unicorns that expose and then break assumptions that I've made. And there's some tricky ones in there that have been, that I'm having to make decisions on that I wouldn't mind some backup on, because there's a lot of sort of philosophical stuff here about content addressing that I feel like I need to have some mind share with. So the first main thing is why pull it apart at all? So Bitcoin blocks are content addressed in the sense that you address these blocks by a hash, and then you can look them up in their system by the hash. But the hash only it's only a pure hash. It's a double SHA-256 of the first 80 bytes. That's all it is. And then you have this internal DAG structure within the block itself, where that 80 bytes contains a hash of this binary Merkle tree, which hashes the transactions. There is an approach you could take where you could say that the Bitcoin block construction is a hash, and that's what we're going to call the hash function. And so that top level hash, even though it might be a SHA-256, we could say, well, it's actually a Bitcoin hash, and that hashes the entire block. So that's one approach you could say, but it doesn't seem to be satisfactory, because that really stretches the limits of what we would call a hash function. But what is a hash function? We went through this recently. We're looking at some stuff for Filecoin as well. What is a hash function? What are the boundaries of what you call hash functions? So if we take the approach of saying, let's say we want to pull this apart into content address chunks, where the content address it comprises the double SHA-256 hash of the chunk, which you can do because Bitcoin uses that to address these chunks. It does it internally. It uses that same algorithm to address all these chunks. So this is a standard Bitcoin block, the old-fashioned simple version of the Bitcoin block, where you would have the header, which is addressed. So you can pull that out as a piece, and then you've got this IPLD-like structure of this tree where each one links to another one. So it's a Merkle in the sense that this thing links to all the other pieces of itself in a contained unit. And so the header links to this binary Merkle tree root, and then in there, or if you traverse the nodes, then you get to the base of it, which contains these transaction IDs, which are the double SHA-256 hash of the individual transactions. And so you can traverse that. The block itself, but Bitcoin blocks in their binary form don't store that tree, intermediate structure. It's implicit because all the bytes are there. You can reverse engineer it so that it's there. But what I'm doing is treating them as blocks. And so I'm creating blocks for them and then storing them, and they're 64 bytes long because they're 2 hashes put together. And so I've got this tree of 64 byte chunks. And then you can actually navigate it with IPLD tooling. You can treat it just like like we do with every other IPLD thing, except it's not our normal DAG form, so you can't like store arbitrary types in there, but you can decode this thing into the same sort of structure that you would for IPLD. So there's a bunch of assumptions packed into that I'm happy for any of you to attack, but that's the top level. Then SegWit came along and messed things up, because SegWit was addressing this issue of people were using the witness data inside transactions to modify transactions in a way that wasn't healthy for mining. People were basically abusing the structure. So they said, well, let's remove the witness data from this top level and let's pack it into another structure. And in practical terms, what that means is that the block is the same, sort of, but it internally contains a different content address structure if you were to decompose it. And what we end up with is, my computer, is this, where we've got 2 internal binary Merkle trees. So we've still got the first one, but the first one only hashes the transactions without witness data. So to make that first Merkle structure and get the TX Merkle root, you take all the transactions, remove the witness data from them, hash them, and then you get their TX ID. And that's the TX ID that you see if you were to go to a blockchain explorer and search for a particular transaction. You could use that TX ID. It's that first level one. But then the witness data is attached, and it's done by hashing the transactions with the witness data. And then that's the transaction hash. So they've got TX ID and TX hash, 2 different things. One's with witness, one's without witness. Not every transaction in a block will have witness data, so those 2 things will be the same for a number of transactions. And over time, more and more transactions have witness data, so we see divergence more and more. So what you do, to create this structure where both of these trees are implicit in the block, but if we pull them out and create separate IPLD blocks for them, then you get this double structure where to get to the second one, you have to go through the first transaction, the Coinbase. And in there's this little field that contains a 38-byte string that is prefixed by a special 6 bytes. And then the remaining 32 bytes is a hash. And that hash is of the heading of this second structure, which is not quite the head of the Merkle root, but it also contains a piece, this nonce, that when you reconstruct the binary form of the block, that nonce actually gets reattached to the Coinbase. So the Coinbase itself, if you were to hash it twice with and without witness data, it would have different hashes because it has witness data in the form of this nonce. And because that's a sort of a self-referential thing, the Coinbase doesn't appear in this second Merkle tree. So you can see the first entry here is just a null hash, which is just zeros. So the Coinbase makes an appearance once, but it does have witness data, which you have to retrieve from here. And then some of the transactions, their full form can only be addressed from the bottom of this Merkle tree, but others will make an appearance in both. So transactions that don't have witness data will make an appearance. Their TX ID and their hash are the same, so they'll make an appearance in both of these Merkle structures. And that, which also means that you'll have some repetition in the internal blocks of that binary Merkle tree. So you can see I've labeled these blocks here 6 and 6 are the same, because it's the same thing. So you do get this compaction that happens by repeating these parts of the structure. So that's what happens when you try and decompose Bitcoin into content address structures where you are unwilling to say that the Bitcoin block encoding algorithm itself is a hash function, which works So I have this all working, and I am decomposing all the blockchain into these things, and mostly it works great, but it turns out that there's a bunch of unicorns which break assumptions. So interesting ones I've encountered so far that I'm having to deal with that do undermine some of this approach. One of them is this little 38-byte string in the Coinbase that says, this is a SegWit block. You're going to have to navigate to this other binary Merkle tree to get the real form of some of the transactions. That does make an appearance prior to SegWit because it's not a non-standard string. It was used, some would say abused, in some transactions, and they appear before SegWit. So you can find that string in blocks that are not SegWit. So when you are parsing out these chunks, and you navigate. So what I do is if I'm recomposing an entire Bitcoin block, I will navigate from the header to the TX Merkle root all the way down the left side of that binary Merkle tree, get the Coinbase, and say, is this a SegWit block? If it is, then I'm going to go and get all the transactions from the second Merkle structure rather than the first, because I know that at the base there, the full form of each will be there. But when you get to the Coinbase and you decode it and you get a IPLD form of it with a CID to this witness commitment thing, there are blocks where it will create a CID that points to nothing because it doesn't exist. And there's no way of knowing when you're decoding whether that thing exists or not. The only way to know is to try and load it from wherever you're storing these things. Say we were storing them in IPFS. You would do this traversal. You get to the Coinbase, it would present this witness commitment thing to you. And then you would have to say, okay, let's try and load it from the IPFS network. And if it doesn't load, it's probably not a SegWit block. If it does load, then definitely is. But that puts the onus on the loading mechanism to fail properly for you, and not just that block happened to not exist in IPFS. In the way I'm storing these things, they will exist. So I know that all the things exist. I'm packing these things together, but that's not guaranteed in a distribution mechanism that they will exist. So the signal for how these things are structured depends on whether you can load this thing or not. Sorry, Volker.
I have a question. Do you then, because if you then find out it's not a SegWit block, but there's a transaction with this ID, right? So if you would load, so if you then load it with the CID of the transaction and you get it back, you know that there was a transaction, not a SegWit block. A SegWit witness commitment thing.
You mean right? if the hash points to something else?
I mean, so you basically request with the CID of SegWit because it has the prefix.
Yeah. And
then you have some timeout, and then you try it again, getting a transaction back.
No, so because the thing is, it doesn't point to a Merkle root, so I can differentiate it. This thing here, like in here, I've got 3 different multi-codecs. They've got the header, which is we're calling Bitcoin block. The transactions and the inner parts of these binary Merkle trees we're calling Bitcoin transaction. And but then the thing that the Coinbase points to is something different. It's called the witness commitment. And so I'm storing them as multi-codec witness commitment.
Yes.
And that means that when I do the load, it's only the CID is encoded with witness commitment. It's not a Bitcoin transaction. So it has to be of type witness commitment for it to successfully load. So that sort of limits the range of the things it can find. So it's a binary, exists or not.
Yes, but if you basically you try to retrieve it and you don't get anything back. The problem is you don't know if you couldn't retrieve it or if it's not there.
Yeah.
That's the problem.
Yep.
But you know when you created the CAD for the witness commitment, you could also create a CAD of the transaction. Because if so, and then try to retrieve the transaction, and if this transaction exists, then it wasn't a witness commitment.
No, you can't, sadly.
Okay.
Because the biggest challenge here is that in the binary forms, the hash and transaction ID don't make appearances because you're hashing the hash of itself.
Okay.
So you can't just construct a CID out of nowhere. You've got to construct it with the information you have, and all we have is this little bit of information. What you do though, if it fails, if you get to the Coinbase, you try and load the witness commitment and it fails, you just back up and say, okay, let's assume this is not a SegWit block. We'll go back to the top of that other binary Merkle, resolve all the other transactions from there, and you'll get you will be able to load the poor form of all the transactions, the non-witness form of all the transactions, which might be like, it's not that that's insufficient, that they contain a lot of information. They contain all the coin values and public keys and stuff. You're just missing a bit of information.
Okay, so see, what happens is you could still, like, it could happen that you have a witness commitment link, basically. You can't load it because it exists, but due to
some reason you
can't. And then you go back, try to load the transaction, and it will succeed, although there is a witness commitment.
So it almost seems like you need branching logic for actually the scheme representation rather than just representing the data model. And this is where, like in the W3C, they love an algorithmic approach. They describe it in the abstract, even like JSON LD parsing with RDF normalization algorithm. It's basically just a 4-step parsing algorithm. And so you need, like in a JSON schema, you can basically do like, if this field exists, then actually it needs to be in this format, or like these are the optional enumeration types. Are we doing anything in IPLD to actually do either the scheme representations, to actually do the scaffolding to build it upon? But then is there like branching logic, like aka like JSON schema have?
So there is in IPLD schema, because that's built in. It's the challenge here, and maybe there's another thing I haven't covered, which is we're trying to encode these things in their byte format so that for a start, the block ID matches what the Bitcoin blockchain uses. So we don't want to modify these bytes. And then the transaction ID is the same. So you can take a block ID from the web somewhere, 00000, la la la, and you can turn that into a CID and then resolve these. And the same for the transaction IDs. You can take them from the web anywhere else. Maybe you're querying the blockchain. Oh, I'll query that in IPLD, and I have the IPLD data. I'll query it there. So we're not making up new IDs. So we have to use the raw byte format that Bitcoin uses, which means we can't insert any other useful information here that would make a branchable schema.
I see. All right. So but at least maybe actually to generate it, actually, is there a schema that actually you can do that does actually have multi-step algorithmic approach? Then, because
that would be nice, but to generate this stuff, it's all just hand coded logic that is just getting out of control because of these unicorns.
Oh, go ahead.
No, fine. Go ahead, Peter.
I was basically going to ask: is the problem really that the schema signaling in Bitcoin is essentially taken by the height of the blockchain? So these unicorns from this height down use this other schema, and from this height up use this the current good schema, and at a future height we'll have yet another schema. In IPLD, we actually don't have an ability to say that kind of thing. We only have, does it parse? It's good. It doesn't parse, then it's a different schema.
Yeah, you're right. And the height information is not baked into the blocks, so we can't use that when we put these blocks independent of each other. There is a time in there which you could use as a signal, but I don't think that's a reliable mechanism. There's not very firm rules about times. Although that's something I haven't investigated very deeply, but you could actually use, if time was more rigorously applied, then you could use time as a signaling mechanism.
Yeah, I think the time specificity is only about 90 minutes. And so because you actually can have unordered, you actually have unordered blocks. There's actually plenty of blocks that actually are out of order time series wide, because actually you allow up to 90 minutes for reconciliation.
So one approach I thought of when I first encountered this was, I thought this really is a unicorn. There's going to be like 1 or 2 blocks with this, because I hadn't, I got through 300,000 blocks before I encountered this problem of the witness commitment looking like it exists but didn't. And so I thought, well, maybe in my, like when I specify this, because I'll write up this stuff in documentation and say, this is the IPLD Bitcoin format, and this is how we do it. And by the way, there is a whitelist of Coinbase identifiers that if you encounter these, then they have a special case. And you could use just the hashes, like you could list, 4 or 5 hashes and say, these are special unicorns. They exist in history. We're putting them aside now because we're post-SegWit. And these are special ones if you encounter them, and then you've got special handling. I still interested in looking at that approach, but it's turning out that there's more than I thought of these blocks.
Yeah, and so in JSON LD world, there's actually such a thing as JSON framing. And I think there's where basically you have the scaffolding of a document that actually things that must be there. But then I think there's a branching logic that says, if these things are here, then you follow this path.
Right. Yeah, well, in IPLD schemas, we have unions which help us do that. But then also the concept is baked in that you should be able to apply different IPLD schemas. The intention is that they will be quickly verifiable because they're block local and they don't require too much processing. And so you should be able to quickly try different schemas to find out. But this is not a DAG CBOR, DAG JSON, DAG anything. We don't have that fun here.
So is I correctly understanding that part of the problem also is this information, it must have been used inconsistently, some part of this block of information in the history of Bitcoin as as humans actually wielded it, right? So you've got this space that was reserved in the blocks earlier in time, and it was used, it must contain nonsense data, or are we encountering blocks where people tried to put low bitrate selfies into the Bitcoin or something? I remember hearing stories about this.
Yeah, so what this little witness commitment goes into a field in their script, and it follows an op return, which is meant to make that's an end of a script ASM. But it's possible to put stuff after the op return, which is nonsense. And so that's where people would embed things in. They could say, okay, op return, but I'm going to put some bytes after that, and that contains my fun stuff.
Right.
And for SegWit, they said, okay, if you find an op return plus 32 bytes, that 32 bytes is a witness commitment. But it turns out that people were inserting 32 bytes after op return.
So right, this is the equivalent of, you're not trying to specify a decoding and a schema for something that was well designed, dare I say.
No.
So it's more like if this was website certificates, we would be looking at a situation where somebody had discovered the encoding bugs where you can put information after a null terminator, and some implementations are fine with it and some aren't. And people,
that's exactly this, yeah.
And then somebody else wrote a spec that uses it even more with different semantics than ever before, and they just pushed it and rolled with it.
Yeah, what we're seeing is the implications. What we're seeing is the implications of a desire not to make a hard fork. This is what happens if you want to do a soft fork and say it's all backwards compatible. That's what SegWit is. Even though every miner now handles SegWit, it was never a hard fork, and it was. This is what happened.
So given all this, and I think Peter's identification also that the Bitcoin is de facto using the block height as part of the versioning here, I think that observation is super true. So I don't know how low granularity.
It's literally true. It's in the code.
Yeah.
There is a block height in the code that says
Oh,
if after this height, then this.
Yeah, this literally how it works, Eric. Like they literally have the schema based on your block height.
Cool.
But
wait,
the block
so
height's not baked into the blocks.
Right. Is this one of the reasons why, in reality, you still have to clone the entire Bitcoin chain in order to reason about it? Is this why?
Yes.
So, yeah,
otherwise
so
you have to trust the actual software you downloaded, that it has baked in a number of checkpoints from the blockchain, like actual IDs, and it says, yeah, from there on, like earlier than this ID, we're good. But if you actually want to verify that your software isn't, being screwed with, you have to start from the Genesis block all the way up.
Right.
And there's a bunch of other information that is useful that you can only get from having the entire chain. There's information about individual blocks that you can only garner by having all the blocks up to that block. And thankfully, that's not a ton of data, but I have in all my unit tests, I have to remove a fixed list of fields that you cannot derive from the blocks by themselves.
That's cool. I'm just gonna try to not engage with the fact that invalidates kind of the core purpose of Merkle trees, but
right. And this is what I'm finding is this exercise is really helpful in figuring out some things not to do. I'm really finding this valuable, and it's also really challenging some of the core assumptions, like this thing of, okay, why don't we just call the block algorithm a hash function?
So I don't know, we mentioned time briefly earlier, and the granularity might be kind of wide, sure, but is it plausible in practice? And knowing that the thing that Bitcoin officially does with the block height is also wildly impure and it's a bit silly, right? So the bar for sanity here is really low. Is low granularity time good enough that we can actually use it as a heuristic for this thing and document that that's what we're doing and go with it?
That's something I can check. Yeah.
Yeah. Unless timestamps are completely erratic random numbers that nobody validates in any way, which is possible, if they have any rigor to them at all, then I would think it is also de facto true, the same as the block height is encoded as true for this, that beyond some date on the wall clock that we've all roughly agreed on, even if it swings by 90 minutes, even if it swings by a day, there should be some line where we can draw where a significant number of clients of the blockchain started considering this 32-byte construction to be magical. And after that date, we should not see any more of these unicorns that are rule breakers.
Yep. That's definitely something I probably should check, because I have the ability to. It does assume that there will be that future blocks will have no ability to make wild times, because perhaps some future incarnation of the algorithm will say, yeah, we've decided this time field doesn't really matter, so you can use it for variation in mining. They've done that with the version string now. So miners were starting to abuse the version string because Bitcoin only takes the last 5 bits of it. And so they were saying, well, we've got these 3 bits at the front, we can vary. So version numbers in Bitcoin blocks are wild unless you consider only the last 5 bits.
Cool.
Yeah, I mean, it's fascinating the things people abuse when you give them the freedom. They've got this strict algorithm, and now all the edges are being found because there's economic incentives.
Oh man.
Yeah, I actually want to bring it back just a little bit to what Eric said, that this is kind of like breaking with the spirit of Merkle trees. It doesn't really, because the schema is defined on the entire DAG, which starts from the root.
Yeah.
And that is completely deterministic. In fact, this is how they rolled it out. it was like they upgraded the software, and in each Bitcoin node, there was a switch in the future at some date that wasn't known at the time, but basically at this height, you start treating the SegWit data as something else.
Yep.
So
yeah, and it is, yeah, we're not, I am pretending a little bit here that these things are in isolation, but the header points to the previous block. So the DAG is the entire chain.
yeah, and that's basically the point I'm trying to make. The way they're actually using the blockchain is correct. They basically had one more switch for the schema type that we currently don't have, but Bitcoin is not the only thing that will have this going forward because, well, compatibility is a thing.
Isn't that sort of taking the arrow the wrong way though? So like if you've got a hash that starts you off with a DAG that's very, very large, like you've got it at the tip of the current and it covers everything, then that reasoning holds just fine. But isn't this sort of a problem where if you take a tip that was quite old, but you don't know that, right? You have no magical knowledge of this. You can't tell.
But you can get that knowledge. You can get that knowledge if you traverse all the way back in time, and then you can tell the height.
Right, but what if you only have information from back in time?
Then you still have, you can still generate the height from that point.
The height is always discoverable. It's part of your DAG. Basically, if you have a complete DAG from a certain point, you can figure out how high this point is.
Yeah. Anyway, shall I continue? Because I have a couple more of these unicorns.
Yeah. Oh boy.
Yeah, and there's a lot to learn here. Let me just remind myself. Okay. So something, and so this approach wasn't, I didn't come up with this approach of saying, let's decompose in this implicit binary Merkle into actual blocks so that we can navigate it as separate blocks. This is in an original Go IPLD codec that Jeremy and some others have written, and so the idea is that you navigate to this binary Merkle. There are all these blocks are labeled Bitcoin TX because you don't know and you can't know whether this thing will be a real transaction or another node in this binary Merkle. You only know once you get there. And so labeling them all Bitcoin TX multi-codec does make sense. So what you do is you navigate in and you resolve a block, you get the block out, and you use the size to tell you whether it's an inner node in this tree or whether it's a real transaction. If it's 64 bytes exactly, then it's 2 hashes jammed together. I can then, and then that's your schema. And then you would say, okay, I return then an array of 2 CIDs. That's how you deserialize 64 byte things. And if you get anything other than 64 bytes, you deserialize it as a transaction format. And so you can do that really nicely. You load these blocks and you signal on the length of them. It turns out though, as I discovered yesterday, that there are transactions which decode, which encode into a binary form of 64 bytes. Very small transactions, but they're exactly the same length as these inner Merkle nodes. So then we have this schema problem of, okay, it's I can't just switch on length. I have to actually start decoding these things and see if they decode properly to tell whether it's a transaction or not, which is possible. But then there's another problem, which is that there are a number of these blocks which start with enough zeros that they will successfully decode one of these inner Merkle nodes as a transaction. And the common one is this, see this number 17 here. They start with 32 zeros, and that will decode you a successful transaction that is basically empty, which sucks. So then the branching logic is, okay, does it decode? Yes. Okay, well, let's have a look inside and sanity check it, because maybe it contains version 0 and all of the structures are 0 length. If so, that is almost certainly not a transaction and probably an inner Merkle node. It's a branch on that. Now, I haven't processed all of the blockchain to know whether that is successful, because maybe there's another unicorn out there, which is a transaction that has version 0 and no arrays, which I don't think is possible, because the Coinbase has to exist in every, oh no, we're talking about transactions. Now, I think in transactions, you have to have a flow of coins. You have to have an in and an out, and these things are arrays. So you have to have at least one element arrays, except in the Genesis block. Oh no, even the Genesis block has an in and out. So I think that's a successful enough check, but the unicorn here is 64-byte exactly length transactions where there's enough bytes in the front for it to decode into a transaction. I haven't encountered a byte. I don't think I've encountered a block so far that is 64 bytes long and has random gibberish at the front that also decodes as a block, as a transaction. That would be surprising, but it is entirely possible given randomness of numbers. So that's annoying. And then what else is there? Oh yeah, no, my other unicorn is more of a formatting thing where I've discovered blocks that only have a Coinbase, which I didn't think was possible. But they exist even later in the tree, later in the chain. And the Coinbase is the thing where the miner awards come in and get distributed. So the miner will take their cut inside the Coinbase and they receive it from the chain in the Coinbase. So there are some blocks that only have miner awards and no other real transactions. But that's not really an IPLD concern. That's more of a decoding concern. So anyway, these are the adventures I'm encountering and keep on encountering. I've done about half of the blocks in the blockchain, but mostly at the front half. And because all this more novelty introduces over time, as there's more randomness as the million monkeys are typing on keyboards in this thing. So yeah, lots of lessons in there, but also just want to hear back to sanity check that I'm not being completely insane by even attempting this. Any questions or comments? Exactly.
Yeah, so we have 4 minutes left. Is there anything else anyone wants to share, say, ask? Yeah, Johnny?
I suppose, do you need to traverse the entire history? Can you actually go back, 300 blocks or 100,000 blocks and just be content that actually, like, we have, everyone agrees that like their earlier schemas are hard to parse, so actually you have it, like, most of the way done?
So I don't really want to talk about explicitly the purpose of this, but let's just say that it's for archival reasons. So the ultimate purpose here is to actually decompose these things into IPLD blocks that we can archive outside of the Bitcoin network. Yeah, the reason I don't want to announce is that it's part of another effort that will have its own announcement. But it's already been partly announced, so it shouldn't be a surprise.
Gotcha. Okay, I got it.
But yeah, the idea is, well, and Bitcoin is one of these things that is probably going to exist for a very long time, because it's like digital gold. Like, unless there's some major flaw found that can't be undone, can't be worked around, probably going to be around for a long time. But it's easier to imagine one of these smaller blockchains disappearing. Let's say Zcash, which it's got some really good properties to it. It's a very useful blockchain, but doesn't have that many users. And there could be a point in, say, the near future where everyone just turns off their nodes, and then all the data is gone. And what we want to be able to say is, well, these things existed in history. Can we store them so that they can be historical records? That's what part of the thinking here. So how can we store them in ways that are useful to traverse? And maybe it's overly ambitious to say we can store them in our conception of what content addressed blocks should be. That's what we're trying, and it's turning out to be an interesting exercise. Because another alternative would be to just say, well, let's just take the blocks out and store their binary form in DAG-PB. You know, that you could do that and just say, okay, they're files.
Yeah, but then what's the point of IPLD, right?
Yeah, and you can't really navigate them very usefully unless you have the file name, which could be the hash, and then that's all you have. But yeah, and mostly this is, I'm finding this is useful for challenging and putting questions to IPLD. Okay, is this sufficient? How are we solving these problems, and what are we doing that is a significant evolution above this conception of content addressing and blockchains and all the other things that Bitcoin brought and tries to use? And it's a good exercise.
All right, so we are running out of time. So thanks everyone for attending, and see you all next week, hopefully. Goodbye, everyone.
We are alone. Does anyone have more stuff they want to talk about?
No,
we're not alone. We're on YouTube.
For me, it shows still recording and live for some reason.
Oh, that's true.